So here's an example where this time you're given a matrix and asked whether a specific value, in this case 3, is an eigenvalue of that matrix. So this is actually a tougher problem than if you're given a matrix and a vector, and the question is this an eigenvector of the matrix? That's a little easier to determine than determining whether a particular value is an eigenvalue. Okay, but so let's think about this. What does it mean for lambda to be an eigenvalue? Well, that would mean that there is some vector x, which that would be the eigenvector that's referred to over here. There's some vector x where the matrix A times x is equal to this multiple lambda times x. So when I think about this definition, I focus more on the eigenvector. So x is an eigenvector if when I multiply the matrix A times that vector x, I get just a scalar multiple of x. That's not something that typically happens if you just grab a matrix times a vector of the appropriate size. Most likely you're not going to get a scalar multiple of that original vector. But so when it's an eigenvector, you do. And we call lambda here the eigenvalue. So 3 is an eigenvalue of that matrix if there's some vector x where A times x is equal to 3 times x. If the eigenvalue being considered here is 3. Okay, well, so that would mean, let's see, the matrix A, I'm going to copy that down, is this one. 1, 0, 1, 1, times the vector x. So if A here is a 3 by 3 matrix, oops, then x is going to have 3 entries because it needs to match this dimension here. So let's call it x1, x2, x3. And we want that to equal 3 times x. So that would be 3x1, 3x2, 3x3. Right? If it's 3 times this vector x right here. Okay. Well, so that would correspond to a system of equations. If I multiply out the left side here, I'll have 1 times x1 plus 2 times x2 plus 2 times x3 equals the first entry over here, so 3x1. And then second row here, so I'll have 3 times x1 minus 2 times x2. So I'm just working my way across the row and down the column. 3 times x1 minus 2 times x2 plus 1 times x3 equals 3x2. And then the third entry here, so 0x1 plus 1x2 plus 1x3 equals 3 times x3. Okay, so the sensible thing to do with that system of equations would be to move over, do like a minus 3x1 to both sides here, and then minus 3x2 to both sides here. And I'm sorry, I'm going to be cramming it in a bit because I want to point something out with the overall pattern here. Notice that what you end up doing is subtracting 3 along the diagonal entries. That might be hard to see the way I've written it here, but let me write it out over here. Or actually, let's just talk about it. So what we end up with is, so I'm going to go ahead and write the coefficient matrix for this. So with x1, we have x1 minus 3x1, so that's negative 2x1. And then these are going to stay the same. So 2x2, 2x3, now it equals 0, because we subtracted 3x1 from both sides. And then, so second row, I have 3x1, negative 2x2 minus 3. We're subtracting 3x2 from both sides. So now I have my negative 5x2. Right? And then 1x3, that stayed the same. And now this is equal to 0. Okay, 0x1 here, 1x2, and then x3, I have x3 minus 3x3, so that's negative 2x3 equals 0. That's my new, here's the augmented matrix for the new system of equations when I move these x1, x2, x3s over. So comparing the original matrix A with this matrix here, just notice that going from here to here, what we did is just subtract 3 along the main diagonal entries. Everything else stayed the same. Negative 2, 2, 2. 3, negative 5, 1. 0, 1, negative 2, compared with this one up here. So that hints at the general method that I'm going to illustrate after this example. But so 3 is the eigenvalue we're considering. We subtracted 3 along the main diagonal there. Okay, and that was based on the system of equations. Okay, so now we need to solve this system. So we're trying to determine if there's a solution. If there is a solution for the vector x, remember we're solving this equation. We're seeing if there's some solution for that vector x, and that would be our eigenvector if we do find a solution, or maybe infinitely many. Okay, so we need to row reduce this to look at our solution set. So I would probably do -1/2 times row 1. So that'll give me 1, -1, -1. Let's set this up a little too big. Okay. Oops, and this is 0 here. Okay. And then I will do, -3 times row 1, add that to row 2. So that'll be 0, and then 3 plus that, so -2, excuse me. And then this will be +3, right? So 3 plus that will be 4, 0, 1, 0, negative, dang it, 0, 1, -2, 0. There we go. And now I'm going to do 2 times row 3, add that to row 2, and then I'll do a swap. So this will be 2 plus -2 and -4 plus 4. And then I'll do a swap row 2 and row 3. This part's dull, I know, I'm trying to get through it. 0, 1, -2, 0. Okay, one more row operation. Row 2 plus row 1. Because, let me say why I'm doing that. So we know now there's a free variable. This is a consistent system. So I know the answer to the first question is yes right now, because at this point I know it's consistent because I see where the pivots are. There's no pivot in the constant column. So the answer here, first question, is going to be yes. Now I want to find an eigenvector. And so when there's infinitely many solutions, because I have a free variable here for x3, then I like to get all the way to the reduced row echelon form rather than use back substitution. When I know I'm going to be writing like a parametric form for my solution set. So row 2 plus row 1. Last row operation. So that'll be 1, 0, -3, 0. -2. Okay. Great. So now we know solution set looks like this. x1 minus 3x3 equals 0. x2 minus 2x3 equals 0. So x1 equals 3x3. x2 equals 2x3. And so any solution for the vector x is going to be x3 is a free variable, x1 is 3 times x3, x2 is 2 times x3. So it's some multiple, some multiple of the vector 3, 2, 1. So 3, 2, 1 would be one eigenvector. That's an answer we could give for this second question. 3, 2, 1 here. Or any other multiple of that vector.